Okay, so how do we find the equation of the normal line to tangent x at pi over 4? Do we remember what a normal line is? What's a normal line?
It's the line
Isn't it like the
perpendicular to the
perpendicular
line that's
bisector?
triangle.
Yeah, it's perpendicular to the tangent line, right? And so how do we find the tangent line? Well, the tangent line comes from the derivative, right? It gives us the slope of the tangent line. So first off, what's the derivative of tangent x?
Secant squared x.
It would be secant squared x, right? So y prime is just secant squared x. And we want to know what is y prime evaluated at pi over 4. So that'll be secant squared of pi over 4. Well, this is the part where you tell me what the secant of pi over 4 is. What's the secant of pi over 4? All right, this is the part where you tell me what the cosine of pi over 4 is.
Root 2 over 2, right?
Correct. So this is 1 over root 2 over 2 squared. Root 2 over 2 is, if we square it, 2/4, right? So this is 1 divided by 2/4, which you just take the reciprocal of 4/2, which is 2. So the slope of the tangent line is 2, which tells us that the slope of the normal line is what?
-1/2.
-1/2. And so that's what we'll use. We'll just say y minus 1 equals -1/2 times x minus pi over 4. This is our normal line, right? What if I'd asked about the tangent line? That would have just been y minus 1 equals 2 times x minus pi over 4, right? Pretend that pi looks like a pi. There we go. True. Everybody agree with that?
Yeah.
Hopefully. All right, cool. So let's real quickly throw up Desmos. We should know what y equals tangent x looks like, right? And we've got y minus 1 equals, I'm going to put in the tangent line one first. So 2 times x minus pi over 4. That's pi over x, not pi over 4. That's better. And so we're tangent right over here at this point, pi over 4, 1. It's hard to, 0.785 is pi over 4. So we're tangent at that point. And if we put in the other one, we should know that since the slope is the opposite reciprocal, it should be perpendicular to it. And there it is. Cutting right through all of those different ones, right? But specifically at the point pi over 4, 1. Good or no?
Good.
All right. What about this one? How are we going to find this derivative? Well, we have two options, right? The first option is this is a function times another function. So we could just use the product rule, right? But our second option would be to simplify it first, wouldn't it? So who would prefer to simplify first and who would prefer to use the product rule? Product rule. Product rule, okay. Whatever you say. First function is cotangent x plus cosecant x. Derivative of tangent minus sine ought to be secant squared minus cosine, right? And then plus, and we'll have tangent minus sine. What's the derivative of cotangent? That's negative cosecant minus cosecant cotangent. All right, that's a mess, huh? What if I wanted you to simplify? What if I said simplify this fully? This would be awful, wouldn't it?
Yeah.
Yeah, that'd be awful. What if we had simplified it first? What if I distributed this out? What's cotangent times tangent?
One.
1, right? That's nice. What's cotangent times sine? Right, that's cosine over sine times sine. That just a negative cosine, right? Because it's a negative sign. What about cosecant times tangent?
Sine over cosine squared.
No.
Oh wait, sorry.
1 over cosine?
Yeah, 1 over cosine, which is what? Secant? And then what about cosecant times sine, or negative sine? That'd be a -1. So really, we just end up with secant x minus cosine x if we simplify it first. And then what is f prime? Looks like secant x tangent x plus sine x. I prefer that answer. And unlikely that they would give you this answer on the AP test, even though it's true and it is accurate. And if you distribute it all out and simplify it and rearrange stuff, you'll get this same answer. But always, if you're looking at a fairly complicated trig equation that you're trying to take a derivative of, always simplify that nasty trig equation first. Okay? So always simplify first if you can, and then worry about taking the derivative after that. Sound good?
Yeah.
All right, cool. All right, let's move on. Let's do one last one. You guys want to try this on your own?
Sure.
Yes.
All right. Ready to go. You have 2 minutes. Simplify fully. So first off, there's not really a good way to simplify this to begin with. So we'll just go right off the bat, taking the derivative using the quotient rule. That'll give us 1 plus cosine x, right, denominator, times derivative of numerator, which is cosine x, minus numerator, times derivative of denominator, which is negative sine x, all over denominator squared. Hopefully you all started with that.
I simplified it to sine x plus sine x over cosine x, which is sine x plus tangent x. Can you not do that?
You cannot do that. I'm going to give you an example of why. Suppose you have something like 2/5, right? Well, that would be the same as this, isn't it?
Yeah.
That does not equal 2 over 1 plus 2 over 4, does it?
Yeah, that's not right.
Yeah.
Okay.
Yeah, that's if you have a single term in the denominator. So like if I have, 2/5, I can turn that into 1 plus 1/5, which is 1/5 plus a fifth. That's fine. But you can't separate out terms in the denominator. Does that make sense?
Yeah.
Okay. Yeah, common mistake. A lot of people try and do stuff like that. Can't do that. All right, so continuing on, we now distribute out this numerator. You get cosine x plus cosine squared x plus sine squared x all over 1 plus cosine x squared. And then what does the numerator simplify to?
1 plus cosine x.
Cosine x?
Yeah, this cosine squared plus the sine squared is just a 1. So now we have a 1 up there plus the cosine x over 1 plus cosine x squared. And we can simplify that into just 1 over 1 plus cosine x. Good or no?
Good.
All right. Everybody feel moderately comfortable with taking derivatives of trig function stuff?
Yeah.
All right, cool. So we're going to now move away from that, although we're still going to use some trig functions today, but that's not going to be our sole concern. We're going to move into some more complicated functions because nothing we've dealt with so far has been, a super complicated function all on its own, or even have really like complicated pieces to it. But now we're going to move into things like, sine to the 5th of 7x squared and stuff like that, where there's like a lot going on within the function. But in order to do that, we're going to start with something real simple. So what we're going to do is we're going to take a very simple function that you know how to take the derivative of, y equals 6x minus 10. You could take the derivative of that, right?
Yeah.
Yeah. And we're going to actually write it out as if it was a composition of two different functions. So I want it to be 2 times something. I want it to be 2u, right? What needs to go in here? This is u right here. What would u be?
3x minus 5.
Right, 3x minus 5, right? If you distribute that out, you get the 6x minus 10. Okay. So you all agree that y equals 6x minus 10 could be written as y equals 2u with u equal to 3x minus 5? Hopefully. Okay, cool. So now I'm going to ask you for 3 different derivatives. First off, the derivative of y with respect to x. So that means go up here and look at the y function that has an x in it. What's the derivative of that? What's the derivative of 6x minus 10?
6.
6, good, okay. Now, the next thing I want is dy du. That means the derivative of y when it's written in terms of u. So what's the derivative with respect to u of y?
Two.
2.
It's 2, right?
Yeah, it's just 2. All right. Now I have another function, the function u. I want to know what's the derivative of u when it's written in terms of x. What's du dx?
3.
3. All right. Now here's the very, very difficult part of all of this. Not really. There is a very, very important relationship between these 3 numbers. What is that? 6 is equal to
2 times 3.
Oh, you guys are amazing. 2 times 3 is equal to 6. You all agree with that? Or in more generic terms, dy dx is equal to dy du times du dx. That the derivative of a function with respect to its variable x is the same as the derivative of y with respect to u times the derivative of u with respect to x. If you take that original function and write it as a composition of 2 functions, a composite function. You all are familiar with composite functions, right? Something you dealt with last year, the year before, or every year since you were like 7 years old. Okay. This rule right here is called the chain rule. Okay. Chain rule is the most important rule in taking derivatives because it allows us to expand out the number of different functions that we can take the derivative of, just by a huge amount. And we can pretty much take the derivative of anything now that we have this chain. Because we can take any really complicated function and write it as a composition of 2 other functions and then use this rule. Okay. There are other ways to write this chain rule out. The most common of them is that the derivative of a composition of functions, right? Sometimes a composition of functions is written as f of g of x. You familiar with that notation? Yes, familiar with the notation f of g of x. Okay, so sometimes we say that the chain rule is the derivative of the outer function, so the derivative of f evaluated at the inner function, so evaluated at g of x, times the derivative of g of x. And that's what we've got here, right? Our outer function is y, and we're taking the derivative of y and evaluating it at u, which is the inner function, and then we're taking the derivative of u. So either way you write it, each of these things is called the chain rule. Here they are, right? And there's this other one in the middle. You're not going to really need to worry about that one so much. But the derivative using the chain rule is dy du times du dx, or it's f prime of g times g prime. So our goal is to be able to take some function and write it as a composition of two functions. And if we can do that, then we should be able to take its derivative. Does that make sense? Or no?
Yes, that makes sense.
Oh, good. Okay, great. So let's give it a shot with something like y equals 3x squared plus 1 squared. Now, this is one that we could distribute out, right? We could write 3x squared plus 1 times 3x squared plus 1, and then do the distributing and then use the power rule. True?
True.
Or we could write it as 3x squared plus 1 times 3x squared plus 1 and use the product rule. Also true?
Yes.
Yeah, okay. So we're not going to do either of those things. Well, we are, but we're not going to do either of those things first, because I'd like to see if we can use this chain rule to come up with the derivative. So how could we write this as a composition of two functions? What would y be in terms of u?
U squared.
Right, we could have y equals u squared with u equal to 3x squared plus 1. Everybody agree that that would make the same thing as 3x squared plus 1 squared?
Yeah.
Cool. All right. So first off, what's dy du?
To
2u?
you.
2u. Okay. What's du dx?
6x.
6x. So what does dy dx equal? It equals those two things multiplied together, which is 12x u, or 12x times 3x squared plus 1. Any questions or issues with that? No? All right. Suppose we had gone through and distributed this out. 3x squared plus 1 squared is what? 9x to the 4th plus 6x squared plus 1, right? Is that true? Yeah, that's true. So what would y prime or dy dx be? It would be 36x cubed plus 12x. And if we distribute that out, what do we get? We get 36x cubed plus 12x, right? In this case, yeah, definitely, probably a little bit easier to go through and just distribute it out, right? But this gives it to us in a nicely factored form, first of all. And second of all, suppose this wasn't to the second power. Suppose this was to the 12th power, right? Well, now this rule is going to be really, really convenient, right? Rather than distributing this out 12 times, we'll just make this a 12th power, which will turn this into 12u to the 11th. And then we'll put it in over here. And it'll change our final result, but the chain rule will make that much, much, much easier to do, won't it?
Yeah.
Yeah, definitely. All right, cool. Next one. Let's take a look at f of x equals the sine of 2x. So if f of x is the sine of 2x, how could we write this as a composition of two functions? We could say y is equal to what?
Sine u.
Sine u with u equal to just that 2x. What is dy du?
Cosine u.
Yeah, cosine u, just the derivative of sine, right? And what is du dx?
Two.
Just 2. So dy dx ought to be 2 cosine u, or 2 cosine 2x. Easy enough or no? All right, I'm going to assume that means it's easy enough. Let's prove that this is true. We could use a trig identity to rewrite sine of 2x. I know that you know what that is because it's on the sheet of trig formulas that I told you to have memorized before we started this class. What's sine of 2x equal to?
2 sine x cosine x.
2 sine x cosine x, exactly. And then this is a product of two functions that could be differentiated using the
Product rule.
product rule. So we'd have 2 sine x u, right, times the derivative of v, so negative sine x, plus the derivative of 2 sine x, which is 2 cosine x, times cosine x. Or if I were to rewrite that as this, I could do 2 cosine squared x minus 2 sine squared x. Well, that sure doesn't look the same as 2 cosine 2x, does it? Could factor out the 2, couldn't I? That doesn't look like it either. But on that same formula sheet that I told you to have everything memorized, what does cosine squared x minus sine squared x equal?
Cosine of 2x.
2x. So that's 2 cosine 2x. This time, not using the chain rule is a little bit more work, right? Hopefully we get the idea though. Any questions or issues with that? All right. Let's do another one. We're going to practice a bunch of these fairly simple chain rule problems, and you're going to have a bunch of simple ones for homework, and then tomorrow we're going to work through some more difficult ones. So I'm given a position function. X of t is cosine t squared plus 1. I want to find the velocity function. So what's the relationship between a position function and a velocity function?
The velocity function is the derivative of the position function.
Perfect. So v of t is x prime of t. And we could write this, and this time our variables are all a little bit off here. So we got to be, we can't just follow the exact rules, we just got to follow the concept of it. So x, or x of t, x is equal to the cosine of, we'll say u. And what does u equal?
T squared plus 1.
And so now we want the derivative of x in terms of u. So that will look like dx du. What's dx du?
Negative sine u.
Sine of u.
Yep, negative sine of u. And then this one, we're taking the derivative of u with respect to t, which should be
2t.
2t. So when we multiply it all together, it should be negative 2t sine of u, or sine of t squared plus 1. Good or no?
Good.
All right. Let's do a few more. You guys want to do this one on your own real quick?
Yeah.
All right. I'll give you guys about a minute or two to do this one, and then we'll try and blow through another 3 or 4 or 5 of these, and then we'll be done. Ready, go. So remember, differentiate just means take the derivative. So we're looking at a function, we'll say y equals sine of u, with u equal to x squared plus x. And what is dy du?
Negative cosine u.
Not negative, positive cosine u.
Cosine u.
Right.
And then what is du dx?
2x plus 1.
So all this is 2x plus 1 times the cosine of u, or the cosine of x squared plus x. Good or no?
Good.
Great. All right, let's do another one. What should we do?
You can have y equals square root of u.
Y equals square root u, because we know how to take the derivative of that, right? With u equal to x squared plus 1. And all we got to do is take the derivative of each of them. This one becomes 1 over 2 root u, right? And this one becomes just 2x. So when we multiply those together, we've got 2x over 2 root x squared plus 1. And it'd be nice to cancel out those 2's, I think. X over root x squared plus 1. Any issues with that? Everybody okay with that one?
Can root x squared plus 1 be simplified more or no?
Nope. Only if you had something in here where it was all multiplied together that was being squared. So if I just had an x squared in there, sure. But x squared plus something else, nope. Unless there's like some factoring or something you might be able to do, but there's not with this one.
Okay.
Cool. All right, let's do another one. How am I going to write this one? Y equals what?
1 over u cubed.
Over u cubed.
We could say 1 over u cubed. We're going to do this one 2 different ways, just for the heck of it. First way we'll do it is like this. What's the derivative of 1 over u cubed? What rule do we use for that?
Reciprocal.
Reciprocal rule, yeah. So negative derivative of the denominator, 3u squared over the denominator squared, which would be u to the 6th, or negative 3 over u to the 4th. Yeah. And then what about du dx? Ought to be 8x plus 6. And we'll end up with negative 3 times 8x plus 6 all over u to the 4th. Good or no?
Good.
All right. Now, we could have also written this if we'd wanted to. We could have said y is equal to u to the negative 3rd power. And then we wouldn't have used the reciprocal rule. We would have used the power rule. And we would have got dy du equals negative 3u to the negative 4, right? Well, negative 3u to the negative 4 is the same as negative 3 over u to the 4th. So either one of those would have been good. Everybody all right with that?
Yeah.
Cool. All right. Let's do one more. I think this will probably be, maybe this will be the last one here. You guys want to try it on your own? And then we'll
Yeah.
got it together. All right, we got a couple minutes, so give you like 2 minutes, work through this one, and then we'll do it together, and then we'll be done for the day. So we've got y equals what?
U to the 1/3.
Yeah, u to the 1/3, right? It's cube root is 1/3 power, so u to the 1/3, u equal to 5x squared minus x. So our dy du becomes 1/3 u to the negative 2/3, or 1/3u to the 2/3. And our du dx, should have written that, dy du dx is just 10x minus 1. And so all we end up with is 10x minus 1 over 3 times u to the 2/3, and u was, oh, sorry, 5x squared minus x plus 4. Forgot that plus 4. U is 5x squared minus x plus 4. Good or no?
Good.
Good.
Cool. So yeah, that'll be it. Tomorrow we'll do a couple that get a little more complicated. Same process, but we're gonna have to use the product rule within it. Reason we're gonna go through these is because some of these require some tricks that you may not be familiar with for factoring to see when they're equal to 0, or you know, when we have fractions on things when they might be undefined. And then we're going to deal with some where we have like a function within a function within a function. So it's the tangent of 4x cubed, but it's also the tangent of u cubed. So we're going to have to apply the chain rule multiple times. So that's the plan for the beginning of tomorrow, and then we're going to get into other derivative formulas and other ways to find derivatives the rest of the week. That should be it. Anybody have any questions at the moment on anything we did today?